Right. Okay, yesterday we were still going through notes and we'd had a look at the strength at which different half cells attract, and we said that the formula that we dealt with, can you remember the formula? E naught of what? Of the whole cell was equal to the E naught of the reduction. In other words, the winner minus the E naught of the one that loses, the loser, which is oxidation. Right, that you've got to write that formula down exactly as it appears on your data sheet when you use it. Right. If you turn to the next page of notes that I gave you, that's the page of notes that starts off saying formula at the top. You all got it? Don't you have that? Right, let's hand them out. There's your formula at the top. Please put it in a box, highlight it, whatever it takes. Thank you. Right. Okay, there your formula is. Some examples: determine the direction of electron flow, as well as the E naught cell values for each of the following half cell combinations. It's done for you. Okay. But just make sure that you agree with that. So if we do the first one, what does it say in your, does it say reduced and oxidized? As I say, it changes every year. Oh, I see what you mean. Use what the data sheet says. As I say, yeah, my apologies. Use what the data sheet says. So if the data sheet says reduction, change it to reduction. And I'm fairly sure that in a year or two's time it will change again. Right, determine the direction of electron flow for the following: zinc, zinc 2 plus. So you got zinc, zinc 2 plus, and iron, iron 2 plus. Right, that's your cell setup. Very quickly, very briefly. Now, who can tell me what's the pulling power of zinc? Minus 0.76 volts. What's the pulling power of iron? Minus 0.44 volts. Right. Which one is pulling more strongly? Iron. That is a bigger number than that. So the electrons are going to flow in that direction. Don't forget, when you show the electrons, write an E negative next to the arrow, because we're dealing with electron current here. Okay, so which one is the winner? This is the winner. In other words, it is the one which is reduced. And this one is the loser, it's the one which is oxidized. And now it's easy to work out. What's your formula? Not E0, E naught. Cell equals E naught reduction, yeah, reduction minus E naught oxidation. The reduction one is minus 0.44. The oxidation one is minus 0.76. That gives you an answer of plus 0.32 volts. Okay, you all happy with that? Just make sure you get the same answers for the next two. Yes, you'll have to come down to my office after this lesson. I'll do it here. All right, does everyone get those answers? It's always a good idea to draw it. Do you agree? Does it matter if I haven't drawn it absolutely perfectly? You've got a fair idea of what's going on there. That's all you need. Okay, I'd like to move on. I'm assuming everyone's okay on that. The next question that I've got for you is, where do these E0 values actually come from? You've all got this table. See, table 4B. I have any more copies of it somewhere? No, I don't have a copy for myself. Okay, now where do the values in table 4B come from? Sorry? No, it's not the same. If you compare that to the electronegativity, it's not the same. Fluorine, for example, has got an electronegativity of 4,0, but the fluorine fluoride half cell has got a reduction potential of plus 2,87. Not the same. You agree? So it's not the electronegativity. It's linked to the electronegativity, but it's not. It was actually obtained by experimental process. What they did was they said, right, let's set up a cell which we know has got a value of 0 volts. Okay? A half cell. That doesn't pull electrons, or doesn't give electrons away, it doesn't pull, it's got no value. Okay? And we connect it to another half cell, which is your unknown one. Let's say iron, as an example. Okay? Let's say we try to test. No, let's not choose iron. That's a bad example. Let's say we go for copper. Our good old copper. So let's say we're trying to determine the value of copper. We're not sure what copper's value is. We connect copper up with copper 2 plus solution. Okay. And we connect it to this half cell which has got a value of 0. Now, we find when we do that, that the electrons get pulled that way, let's say. Now, what does that tell you? Copper is pulling more strongly or less strongly than this half cell? More strongly, okay? So they go and put a voltmeter in there. which is really measuring the E naught for the cell. Do you agree? And they get a value of plus 0.34 volts. Okay, they get a value of plus 0.34 volts. What does that mean? Well, what's your formula? E naught of the cell is equal to E naught of the reduced, is reduction, whatever, please just bear with me, minus E naught of the oxidation. What does the E naught cell work out to be? Plus 0.34. That's what it's reading, isn't it? Okay. Is equal to the E naught of the one which is reduced, which happens to be the copper 2 plus. It's been reduced because you can see the needles pointing that way. Right, you happy? Minus the E naught one of this, and what's the E naught value of that? 0. What does that tell you? That copper, therefore, the E naught value of copper 2 plus equals plus 0.34 volts. Right. So the problem was they had to find something that had an E naught value of 0. And there's nothing that's got an E naught value of 0, or they don't know. So they just had to randomly say, let's choose one. Let's give it a value of 0, and they chose the hydrogen half cell. Okay? So the hydrogen half cell was chosen, and arbitrarily means for no real reason, it was just so. We had to choose one, so we chose it. For example, if I had to say, I'm going to choose one of you who's going to collect the test papers in at the end of the test. And I'm going to say, it's you, Sherwin. There's no reason why. Not that I don't like Sherwin. We know I don't like him, but that's not the reason. It's not because Sherwin's particularly good at collecting in papers. It's not that Sherwin's naughty and needs to do any extra work. There's no reason. It's normally who are the people who get to hand out the things? The two on the ends, am I right? Will you hand out this note? Will you hand out that? There's no real reason. It's just that you're the nearest. Okay, I very seldom say to Esther at the back, will you hand out? Because she's right at the back. So it's arbitrarily done. That's what arbitrarily means. For no particular reason, hydrogen was chosen and given a value of 0. They then linked up every possible half cell that you could dream up of. So dream me up a half cell. Choose any metal that comes to mind. What? Mercury? Mercury 2 plus. There you are. Mercury 2 plus. So you'd need to somehow either get a mercury plate. Can you do that? No. Can't get a hydrogen plate either. So what they do is put mercury in a little cotton bag. Okay? Tie it in the bag. The mercury won't leak through the bag. Put a wire in it, etc. And then a mercury salt dissolved around it. How do you get a hydrogen plate? Bottle of hydrogen gas with a wire in it. Yes. That's more or less how they've done it. So if we have a look at a typical hydrogen electrode, let's show you what it looked like. Why is this coking not wiping off? You check that screen, do you? Is it all off? It's not really all off, but let's see if my magic cloth works better. Yeah. Okay, what they had to do was set up a half cell, which was a hydrogen half cell. So they had a beaker. Okay. And into that beaker they had a special glass container made that had an outlet. Okay, and through that glass container was a wire, and at the bottom of that wire was a little platinum metal plate. Now platinum was used because platinum is almost non-reactive. It's like gold, it doesn't react. So you had a little platinum electrode made there. Okay, then just with a rubber tube, brought a rubber tube in through which they pumped what? Hydrogen gas. Let's put that in blue. It doesn't erase. H2 gas. Okay, and the H2 bubbles would bubble up around the platinum and bubble out through there. Then you'd need a hydrogen positive solution. Am I right? H plus aqueous. Do you want to tell me where you're going to get an H plus solution from? An acid, yeah. So you'd use an acid. And that is your hydrogen electrode. Okay, so you've got pure hydrogen and you've got H plus in contact with each other. You do need a surface where any reactions and swapping of electrons can take place, but platinum provides that surface. So that's what a hydrogen electrode looks like. So they would set up that hydrogen electrode. What would they connect it to? A voltmeter. And then they would set it up with whatever half cell you wanted to test. James said, there's your bag full of Hg. Hg2 plus solution, whatever mercury salt. Give me an example of a Hg2 plus salt. HgSO4, yes, okay. And that wire would be in the mercury there, right? And what is missing? The salt bridge. Could anyone tell me a typical solution to place in that salt bridge? KCl, KNO3, sodium chloride. Just use sodium chloride. Okay? We usually don't use a salt that contains an ion which is present here or there. So I wouldn't use mercury chloride, for example, because that could affect the concentrations. Right, and there we are. But to be able to do it, we said what does affect the readings? The concentration. So what would the concentration of this have to be? 1 mole per decimeter cubed. What would the concentration of this have to be? 1 mole. So any solutions must be at 1 mole per decimeter cubed. What else? No, surface area didn't have to be set. The temperature had to be 25 degrees centigrade, and there was one other requirement. The atmosphere, or the pressure of any gases that were present. Do we have gases present here? That had to be at 1 atmosphere. We'll look at that again in a moment. Okay, we'll get to that. So there we are. That would be, what would we say are the conditions that we've done it at? Standard conditions. That's why if you look at the heading at the top of that table 4b, it says standard reduction potentials. If you were to do it at 30 degrees, you'd get another reading. It wouldn't be a standard reduction potential. That would be a reduction potential at 30 degrees. Okay, but if it says standard, it means it's done at 25 degrees. Right, and then they would just change this. They'd take the reading, okay, fine, and obviously whatever your reading is, it works out to be whatever, well, you just use your formula, and you'd either get a positive value or a negative value coming out of it. So simple, easy, that's how they got it, and that's how they did it. Literally, lab technicians would have sat for years creating different half cells, linking it up to the hydrogen half cell, getting the reading, do the calculation, add it into the table. And people still do it today. If you have a look at some of those half reactions, there's some weird ones down at the bottom. with sulfates and, am I right? Okay, you can use anything. How you actually get it to happen in practice is a little bit more challenging. Okay, obviously if you're doing zinc 2 plus, that's easy. Zinc is easily available, easy to work with. Zinc 2 plus, easy available. But how do you do SO2 gas? You once again have to use a platinum electrode and all of that type of thing. Okay, so you all happy with that? Good. Let's give you the notes that pertain to that. The notes are not quite right, so you're going to have to make some changes to the notes. What is what? That is looking at it from a slightly different perspective. Just ignore it. I'm not teaching it to you from that angle. I'm teaching it to you from the angle of table 4B. So we work with table 4B, okay? Just ignore table 4A. I'm not going to go into the exact differences, but some pupils who use different textbooks, they would work with table 4A. Right, if we read through those notes, where do these E naught values in table 4B come from? H2 stroke H plus was arbitrarily given an E naught value of 0. Any half cell which attracts electrons more strongly were given a positive E naught value. Any half cell which attracts electrons less strongly were given a negative E naught value. And there's a sketch of a typical setup. Okay? Notice you've got a standard H2 H plus half cell. The temperature is 25 degrees. Concentration is 1 molar. And any gases are at 1 atmospheric pressure. What is the error in that sketch? Look at the hydrogen gas. It's meant to come in at the bottom. Gas doesn't just push its way down through liquids, okay? It's got to bubble in at the bottom over the plate, and that is the outlet point. So just change that diagram if you don't mind. Right. All happy? You changed that diagram? No. Yeah, okay. Right. Now, an abbreviated way of writing a cell. Do you agree? It's a bit of a pain to have to go and draw the diagram every time. So, let's see what we can do here. Okay, so we must avoid blue and red. Yeah, they replaced the cokies yesterday when they came to fix the sound that wasn't recording. And no, it's the same make, but it's not working. Okay, let's say, so we can just note here an abbreviated way . So as an example, let's say we've got copper, zinc, zinc 2 plus, copper 2 plus, salt bridge. Okay. Now that's so far, that's about the only way that I could explain to you how to illustrate what the cell looks like. There's another way of doing it, and that is known as your abbreviated or standard cell notation. It's the UPAC cell notation. Where else have you come across the word UPAC? Naming of what? Organic compounds. Now UPAC is the body, worldwide body that regulates scientific naming of things, illustrating of things, how it's done. Okay? So UPAC says that you always start off with your anode, even though your diagram, which one of these is the winner? Now how do you know? You don't know, so you've got to look them up. So quickly look them up. What's the pull-in power of copper 2 plus? Okay. What's the pull-in power of that? Okay, right. Which one's the winner? So if that's the winner, it's the one that's going to undergo reduction. So is this the anode or the cathode? Red cat. Okay. So this is the cathode. And that obviously makes this the anode. Now, have I drawn the anode on the left? No. And I can set it up any way in a lab that I want to, and I can draw it any way that I want to. But when I do it in cell notation, the anode must always be written on the left, and the cathode must always be written on the right and separated with a double line. What does that double line represent, do you think? The salt bridge. Okay? That represents the salt bridge. What you also do, you also always start off with the neutral substance. Now, which is the neutral substance in the anode? So you would start off with zinc, followed by the zinc ion. And you show the two separated by a single straight line. Zinc 2 plus. Then your zinc 2 plus is connected to what? Via the salt bridge to what? Is it connected to the copper, or is the zinc 2 plus connected to the copper 2 plus? Okay, the liquid is joined to the liquid, isn't it? So salt bridge to your copper 2 plus, single line, the copper 2 plus is linked to your copper. So you start and end with your solids. Okay? On the left is always the anode. On the right is always the cathode. You separate the one half cell from the other half cell with a double line, which represents the salt bridge. You separate the solid from its salt with a single line. Right? Are you happy with that? Okay? What you will usually also see is solid, aqueous, and in some cases you'll also see the concentration, 1 mole per decimeter cubed. Okay, this is aqueous, 1 mole per decimeter cubed, and that is solid. Right, and in some cases you also see written over here 25 degrees centigrade. Okay, so that tells you any solutions are at 1 mole per decimeter cubed. Total concentration, temperature was 25. Are there any gases present? No gases, so therefore you don't have to state any pressures. Okay, how would you do this one? Which one is the anode? Which one is the cathode? Do we have Hg in your table? Okay. What does Hg pull with what force? plus 0.85 volts. Hydrogen, 0.00 volts. So which one's the winner? This is your winner. This is reduction. It's going to get the electrons, it's going to gain the electrons. And this is there for your cathode. And this one is there for your anode. Right, so now you know which is the cathode, which is the anode. What does the rule say? Which one do you write down first? The anode, starting with any solids. You have a solid. What is your solid? Yeah, is actually the H2, the gas, isn't it? But you've got the platinum, so you write it down as platinum. So you still start off with a solid, comma, H2 gas. Okay. What's your platinum H2 gas in contact with? The neutral in contact with its ion, which is single line H plus. Double line, what's the H plus solution in contact with? Hg2 plus. Single line Hg. Now let's just fill in the details. Platinum is a solid. The hydrogen is at 1 atmosphere. This is aqueous and it is 1 molar. Right? This is aqueous, 1 molar. This is? No, it's liquid. And the whole lot would hopefully be at 25 degrees centigrade. Let's just check if we've met standard conditions. Is it at 25 degrees centigrade? Yes. Are solutions at 1 mole per decimeter cube? Yes. Any gases, are they at 1 atmospheric pressure? Yes. Did I write the anode on the left and the cathode on the right? Yes. Okay. All these other little bits and pieces, especially that and the concentrations, not critical. Okay? Because you don't always do it at 1 molar. You don't always do it at 1 atmospheric pressure. You don't always do it at 25. But if they say it's a standard cell, then you put that in. Right? Happy with that? Okay. You've got that note. That rule at the bottom of that page, cross it out, it no longer applies. It was a stupid rule, caused confusion. They've since taken it out. Yes. Is it? I have no idea. Ask Charlene what the French word for hydrogen is. I thought it was universal, that we kept, that for example, Afrikaans calls oxygen suurstof, but they haven't made it an S. Okay. Is H. But you still use H. Yes, I don't know why France have changed, because I mean, in French, lead is plomb. Okay, plomb. And therefore, the abbreviation is PB, from plomb, P-L-O-M-B. But we haven't changed the abbreviation because we're English to L. We've kept it as PB. So it's strange that they've changed hydrogen. Just double check with her what they call hydrogen in French. Why is silver Ag? Where's silver mainly mined in the world? The biggest country for mining silver? Argentina. And the Latin name for silver is argentum. That's where Argentina gets its name from, argentum. They go back, it's historical. Yeah. Gold is aurum. The Latin for gold is aurum, meaning the sun. Okay, shines like the sun, glitters, and hence AU. Okay. Someone whose surname started with a K, probably. No, the Latin for potassium is kalium. K-A-L-I-U-M, kalium. Okay, and that's why. Right, for some homework, I'm going to give you some cell notations. I want you to draw the actual picture, and I want you to write the cell notation, and I want you to work the E0 cell value out for them. Okay? So let's put that up on the board. Homework. Right, people, I think it is break time. Okay, right, good afternoon.